There we go.
There we are. Hi, Ricky.
Hello.
So thanks for having me at the conference.
It's a great pleasure, Doug. We're very glad you could join us for the Australian Accessibility Conference. Now, what are we going to talk about today?
I thought we could talk about making data visualizations accessible.
That sounds like a very challenging topic. What have you got for us?
Let's see. All right, let me just share my screen here. All right, how's that look to you?
Excellent. Sensors working overtime.
Indeed. Anybody out there catches the XTC reference, you get bonus points.
I do.
Excellent. But what we're really talking about is making data visualizations, making experiences for people that use different senses when you don't necessarily have vision up for grabs. So just a little bit about myself. I'm Doug Scheppers. I work at Phys Studio. And there we are. I've been coding SVG and JavaScript since around 2000. I've been coding since I was 12, which is, oh gosh, at least 10 years ago. Let's see. I worked at W3C for 10 years. I was the sort of project coordinator for the SVG working group, web apps, web audio, etc. I had a minor role in some of the accessibility stuff like WAI ARIA and WCAG and ATAG and other accessibility standards. And I'm the founder of Phys Studio, which is an accessibility startup, specifically an accessibility data viz startup. We have a charting library called Phys Charts that makes accessible charts, as you might expect. And I also do a lot of consulting on making data visualizations accessible. So I've been thinking about this problem for a long, long time, and I've got some interesting thoughts and some interesting solutions. So first off, I'd like to go into what is a data visualization. Data visualization, you hear this term, and it's just a fancy word for charts and graphs and diagrams and maps. It's often abbreviated, as data viz. There is a common metaphor that people use when they're talking about data viz, and they say data visualizations are a story about data. And that's true. They are a story about data, but that's only one metaphor. I prefer to use a more functional metaphor. That is, data visualizations are a user interface for data. Right. My goal today is to get you to rethink what a data visualization is. And so data visualization, many people think that you can't make data visualizations accessible, truly accessible. When I first started talking about this in 2009, there were many people who said data visualizations are inherently visual. You can't make them accessible. You can add alt text, but that's the best you can do. I look at it differently. First off, I think that data visualizations are assistive technology. What do I mean by that? So if I showed you a spreadsheet, and I've just popped up a spreadsheet on the screen here, and it has the population of the 4 largest countries on Earth: Brazil, China, India, and the United States. Over the past, from 2000 to 2016. And it's just got the rates of population or the numbers of population. So this is a spreadsheet. Now, Ricky, actually, I'm going to ask you, looking at these really quickly, which of these has the highest rate of growth in population? Brazil, China, India, or United States?
Wow, that's going to take a little bit of calculating out there. The difference between the different cells over a period of time. That's
right.
I mean, I could work it out, but it's going to take me a little while to do that.
So let's give you 5, 4, 3, 2, 1. Okay, let's try something else. Let's look at a line chart. Now, can you tell me which one has the highest rate of the highest population growth? Not the highest population, but the highest rate of growth.
Well, it looks like India has got the big steep going from a lower base than China and ending up almost level with it there. So over a fairly short period of time, it's probably had the greatest increase out of those four.
That's exactly right. Um, and that this line chart showed you in just instantly, almost instantly, there was a little bit of cognitive processing of it, right? You had to think about it, but you were able to almost instantly apprehend the answer to the question, right? And if
Yeah,
it were a
yeah,
simpler question, like what's the highest number, right? That would have been even faster, right? That would have taken almost no effort whatsoever. It's China because it's the highest one, right?
sure.
So you see how this is a cognitive accessibility technology, right? There are people who could look at the big block of numbers on the left here and see the answer to that almost immediately. Those people exist, right? I'm not one of them. I don't think you're one of them, right? Uh,
Nope.
the data visualizations are assistive technology. They are cognitive assistive technology. Um, it helps us to think about and notice patterns. It aids certain kind of cognitive disabilities and low vision. Uh, my good friend Wayne Dick, who's a professor of mathematics and who himself has low vision. I was doing this presentation and he was in the audience, and I asked the same question I asked of you, and he immediately piped up with, "It's the green one." He couldn't read what the green one was, right? But from a fair distance, he could tell, oh, it's the green one, right? And he couldn't read the numbers, right? But immediately, as a person with low vision, the data visualization was actually better for him than the big box of numbers, right? So another thing that data visualization helps us do is it helps reduce the effort for someone to consume the information, and it also helps catch people's attention in this data flooded world. But really what it's doing is it's creating a functional model of the data in the minds of the audience. And so that's what we're going for here. There's nothing inherently visual about that. So Ben Schneiderman is a pioneer in HCI, human-computer interaction, and data viz. And he said, the purpose of visualization is insight, not pictures. And you might see Ricky laughing. There's a little image here on the screen of Ben Schneiderman, his head Flapping. I've animated it so his head is flapping like a South Park cartoon. So why is it visual then? Why does data visualization work at all? Because the visual channel is 10 million bits per second. That is an enormously fast throughput. 30 to 60% of our brain is dedicated to visual processing. I'm sorry, 30 to 60% of the brain, of the sensory processing of the brain, is dedicated to visual processing. And there's something called fast visual response. The common evolutionary phrase is seeing dinner or being dinner. It's the difference between whether that snake gets you or whether you get that snake, right? And some parts of that are not even cognitive. They're not even mental. There's actually physical reactions that happen before any of this stuff happens to us cognitively, right? So for comparison, touch takes up about 8%, hearing takes up about 2% of our sensory processing. And the other thing about vision is that it's also multi-channel. We do something called the saccade, and that means that our eyes are constantly shooting around the room, updating the mental scene that we have in our minds, right? Vision is actually happening. It happens in the brain. It doesn't happen in the eyes. When we think that we see a whole scene, I think I'm looking around this room and I see the whole room. In fact, most of that is my memory of the room, and the foveal vision is about your thumbnail at your arm's reach. That's all you are seeing at any given time. But your eyes are constantly shooting around and updating the scene, and your brain is reconstructing an image. Like when they have those photos where they reconstruct a church from the photos of all the tourists, right? That's what's going on in our brain all the time. There's also something going on that the brain allows parallel processing through vision. We can actually process multiple different parts of a scene at once. And you can't really do that with serial sort of piecemeal interactions with data. So in short, it's visual because it helps us to detect, match, and make sense of patterns. That's it. So there's another aspect of this called the picture superiority effect, or the pictorial superiority effect. And again, this refers to how much of our brain is dedicated, how much of our sensory processing is dedicated to vision. And it's an enormous amount compared to other senses. And it also helps with memory retention. So it helps us to quickly see something and to retain images. I have a lot of images on my slides. A lot of people have images on their slides. Why do we do that? Because if I gave you this presentation and it didn't have referential pictures, not just a picture of a cat, but something actually relevant to the information that I'm trying to convey, the memory retention, Ricky, if I asked you details about this presentation, for the slides where there are images, after 3 days, you're going to remember about 10% of that. For the slides that do have images, you're going to remember about 65% of that, right? That is profound. That's a big cognitive change, right? A big cognitive difference. And this effect increases with age. So we think, oh, little kids need things with pictures. In fact, yeah, they do while they're starting to build up their model of the world. But in fact, as we get older, we get more and more dependent on visual things as opposed to text or sound. So if you want to read more about this, you can read it by, there's a guy named John Medina. He wrote a book called Brain Rules. And I'm going to move this. I don't know if y'all can see this, but I can see this little image over here of the Zoom chat. So I'm moving it over, hopefully out of the way. So what we need to do is we need to provide affordances that are equivalent to the experience that a sighted user. We need to provide similar affordances for people who use screen readers to give an equivalent experience. So affordance and equivalence is not just a long lost Jane Austen novel. Thank you, Rick. I worked really hard on making that screen cap on that book. There's a picture of a book by Jane Austen, Affordance and Equivalence. Of course, it doesn't exist. So each feature of a chart includes an affordance and a set of tasks that it's geared towards. Ricky, do you know what an affordance is?
Not really.
Okay, so an affordance is, the way I say it is something that allows you to discover a feature of something and to, at the same time, discover how to use that feature. So if you walk into a dark room, you've swung the door open, you probably want to turn on the light to see something. What do you do? First thing.
Reach out for where I think the light switch is.
Where's that light switch probably going to be?
Round about mid-arm height and just to one side of the doorway.
To the side of the doorway, the opposite of which the door opens, right?
Right.
Right. You could, if you push the door open, they could put the light switch behind the door. I've seen that happen, right? For whatever reason, but it's not a good affordance, right? By making it right there, right where most people are going to reach first, you discover it, discoverability, right? And then as you're feeling for it, right, you feel that the switch is in a position that that you need to flip it up, and it has a freedom of movement to flip it up, right? And so that is part of affordance, right? You've discovered not only the thing, the feature, right, but you discovered how to operate it. Now, of course, obviously, familiar patterns, you know, are going to be used there. But if it were a push button, I could adapt with that. If it were a dial, I could adapt to that, right? All of those are affordances, and the affordance is that it moves. There's a degree of freedom of movement, and so the affordance, even if I'm not familiar with the exact thing, do as much as is familiar, put it where it's easily found, and then make it obvious how to use it. So that's an affordance, right? So with charts, we aren't born understanding charts. We learn them. But once you learn a few common patterns, like height means the amount, right? Whether it's tall or short. If it's short, it means a small amount. If it's tall, it means a large amount. So those are affordances that are used. And if I flip the bar chart on its side, that's not a problem for you. It's the length as opposed to the height, right? But you still get it. And I could make that chart diagonal, or I could make it a bunch of stacked cars or stacked people, or there's any number of ways in which I could make variations on that, right? But because you've learned some basic rules, that affordance gives you that you can discover how to use that chart. You can discover how to map that to data, right? So each feature of a chart includes an affordance and a set of tasks that it's geared towards. So line charts, bar charts, pie charts, scatter plots, each of these, some of them have common features like the X and Y axis, but each of these is an affordance to let you know how to read the data. So for each affordance or task that we have, we need to isolate the channel, that is, say, the means of conveying the information, and the mechanism, and find an accessible equivalent. And we need to reduce the cognitive load as much as possible and anticipate the user's needs. So we need to have equivalent affordances with different sentences. So things like haptic memory, touch memory, echoic memory, sound memory, and textual memory, which is a whole other thing, right? It's related to echoic memory, but it's different. I might talk about those things a little bit later. So there's something called the fast and slow mind. And the fast mind, it's called system 1 and system 2. The system 1 is fast, right? It is automatic, it's frequent, it's emotional, it's stereotypical or stereotypic, it's unconscious. This is where unconscious bias comes in. And there's something called pre-attentive attributes and Gestalt principles. These are immediate things that don't cost extra cognitive load. Then there's the slow mind. It is slow, effortful, infrequent, logical, calculating, conscious. It's Ricky, when you saw that line chart, you saw that line go up. You saw the rates of the lines, and those things you immediately apprehended. You didn't have to think about those. But what those meant, right? And like when you calculated, well, what does that mean for the rate of growth, right? The rate of population growth. So the first one was just, you got the image of the chart for free, right? The second one, it took you a moment to like, okay, the line is sharp. Okay, that must mean, so you were using system 1 to consume the chart. And then you used system 2 quickly, but still slower than system 1. You use system 2 of your brain to interpret the chart. It's thinking about meaning. So when you have a data visualization, when you have a data visualization, it conveys the properties of the data, and for system 1, and then system 2 lets you explore and think about the data. But when you are using a screen reader, for example, you have to use system 2 for both the slow system, for both consuming the data and thinking about it. And this is mentally taxing, and it slows your task performance. So we really have to try to get past that if we can. And all of this is towards a need to reduce the speed and effort needed to accomplish tasks in a non-visual way. So that's what we're looking for here. What we're looking for is not just to convey the data, but to reduce the effort that someone has to take in order to consume that data. Am I making sense so far?
Yeah, very much so.
All right. That's a change. All right. So what are the basics? The basics of accessible data visualization. If you take away nothing else from this talk, take away this. First off, I'm going to be talking a lot about non-visual data visualization, but as I alluded to, to low vision, and there's color vision. A lot of the time, when you see something talk about accessible data visualization, people are talking about the colors that you use. Don't use red and green. Blah blah blah. You can find this advice anywhere. I would say don't just think about a color safe, color palette or colorblind safe color palette. Think about how effectively you are communicating ideas with color, right? And of course, provide another means beyond color for making distinctions. But when we're talking about screen readers, we really need to think about the information that we're conveying just beyond things like color, right? So for screen readers, and for everyone, in fact, you need to provide a summary. Now, that said, this is easier for static charts on your website than dynamic ones, right? If you have a dynamic chart, that's an additional challenge. But especially if you're doing a report or something that has a static site or static data visualization, a static chart, think about what that chart means and how to convey it. And compose the alt text like you're describing the chart to somebody over the phone. Like a lot of people struggle with but how do I write an effective, description of this chart? You can, if you stop thinking about it as an accessibility issue and think about it as an issue of, I'm talking to my boss and I'm trying to report something about a chart that I'm looking at, say it like that. That's how you should convey it. And that's what you should write down for your alt text. Amy Cecil has, with the Data Visualization Society, has a great blog post called Writing Alt Text for Data Visualization. And her takeaways are the alt text should say chart type of data where reason for including chart. For example, a bar chart of or a line chart of population growth for where the rates of population are India. The rates for growth of population are India, China, United States, and Brazil, in that order, something like that, right? And the reason I think it's valuable to have alt text where you can is because you don't want to waste the time of your users, in your readers, if they aren't that interested in the data. Don't make them guess what the data is going to say. Tell them what the data is going to say. And then if they want to drill into each individual data point, let them do that, right? You need to let them do that because they want to draw their own conclusions from the data. But if you can, you should provide alt text straight out. These are the absolute basics with data visualization. And she also says in her presentation, and I agree with this, include a link to the data source somewhere in the text. So it might be that somebody who's using a screen reader wants to use Excel or some other program that they're comfortable with to get the data. And also, this is not just for people using screen readers. This is for anybody. I might want to take your data and mash it up with data from someplace else, right? I might want to take education levels and match that up with voter patterns. So if you give me a link to your data, I can do that. If you just give me an image, I can guess at it, but I can't really do it. So that said, I want to now drill into some of the sensory affordances that we can apply here. So apart from the very basics. So let's look at exploring a data visualization. All right. So this is a toy screen reader that I made. This is not a real screen reader, but it's good for demo purposes. Let's show how a screen reader user might hear some data.
Chart, time spent on creating a presentation, options. Press 1 for chart statistics.
All right.
X-axis, weekdays. 4 items, ranging from Saturday to Tuesday.
So the first thing I'm doing is I give the title, right? I'm establishing the context for the chart. I give the title and I say what each axis is, right? The x-axis and the y-axis.
Y-axis, hours working on this presentation. 12 items, ranging from 0.
All right. So I give the x-axis. I tell you what's on the x-axis. I give the y-axis. And now they understand the context to think about the individual data points.
Saturday, 8 hours. Data point 1 of 4.
Okay, what's notable there? I give the number and I say, expect that there will be 4 of these things, right? Just like with a list item, a list in HTML, it's just like a list.
Sunday, 6 hours. Data point 2 of 4. Option. Monday, 4.5 hours. Data point 3 of 4. Options. Tuesday, 12 hours. Data point 4 of 4.
Okay, so that's when you want them to drill into the data, right? So anybody making a data visualization can do that. I have examples on my blog, on the Phys Studio blog, of exactly how to create in SVG the ARIA and the SVG, et cetera, how to hook that up so that you can make a data visualization. At the bare minimum, your charts should give them access to the data. And if at all possible, give a summary of the data. All right. So it's not that hard to do. Another way of doing that is you could provide a data table. It's still, if a data table were as accessible as a chart, we wouldn't have a need for charts, right? We wouldn't use charts for sighted people. But at the very least, you need to give them serial access one by one to those data points. So that's still, if I have to listen to a whole lot of bars or lines or pie slices, etc., that's going to increase my cognitive load, right? If I'm a screen reader user and I'm listening to this, I'm having to hold a lot of information in my head. Cognitive load is how hard it is to, how much mental processing you have to do in order to understand the message, right? So there are several types of cognitive load. There's what's called the intrinsic cognitive load. The intrinsic cognitive load is just the essence of the information itself, the stripped of any other context or anything like that, right? It's just the information you're trying to convey. And then there's the extraneous cognitive load. Extraneous cognitive load is the cognitive load. It's all of the stuff that's around the chart. That's around the information. It could be distracting things on the chart, or fancy colors, or an ad that's blinking over here, or all the other or your dog that's barking, your cat that's jumping in your lap, whatever. All of that stuff is extraneous cognitive load. It's all taking a toll on you understanding a message. It's clutter, it's redundancy. But there is some part of that extraneous cognitive load that is, especially redundancy and things like this, that is what's called germane cognitive load. It's all the context that you need in order to really understand the core message. So germane cognitive load is the brain looking for patterns within the clutter to develop context. And serial tasks cost more cognitive load than parallel tasks. In other words, when we look at a chart, right, we see all 4 things at one, all 4 bars at once, right? So we understand we are going from the whole to the parts, right? We're building a mental model going from the whole to the parts. When you have serial access, 1 bar at a time, it sounds great that we give them this data access, but they are having to build up a mental model, the part to a whole, and that actually causes more cognitive load. So, excuse me. So processing text by itself introduces additional cognitive load and effort, exertion, right? So we want to reduce that as much as possible. So we can't get away from having text, right? But we do want to reduce it if we can. So here is an example. I believe I wrote this back in 2013. I believe this is the first sonification written with the Web Audio API, which is a piece of web technology that lets you make sounds from numbers, right? So let's take a look. So here is a sonification of the stock market from 2007 through 2011. I'm just going to mouse over it. Okay, now let's stop that terrible sound. But I hope that you saw. So if you're looking at the screen, you see a slow rise, or actually a fairly rapid rise, and then a sharp plummeting sound, sharp plummeting line that slowly starts going up again and kind of falters, and then it peaks, and then it goes down again, and it goes up again. And of course, this is the stock market crash of 2008, 2009. And but you could hear, let's just listen to it one more time. Oops. Well, maybe we can't. We're not going to be able to. But basically, you could hear the tone rising and then plummeting deeply, right? And then slowly rising again, right? As I moused over. Of course, mousing is probably not the best modality, but it can be useful. So that's sonification. Sonification is the non-textual representation of data as sound, right? Ricky, were you familiar with sonification before?
Not really. I've come across the term, and this puts it into a very clear context for me now.
We use it all the time. Geiger counters, EKGs or EEGs or whatever, you know, toot, 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 right?
Yep.
We're really familiar with it, but it can actually be really useful to a non-sighted person to explore some data. So the thing about sonification is it is a really interesting and effective and kind of cool technology, right? But it is great for giving a gist, an overall impression, right? And it's good for identifying trends or outliers, but it is not good for precision. Just like with color, we have we have excellent color vision, but when we're comparing two color regions or two colored things in two different places, we're not good at doing match for match colors, right? We can only have our palette for doing match for match colors is much smaller than our palette for actually distinguishing colors themselves, right? So we have difficulty mapping the semantics to small differences with sonification and with colors. So for precision, we need text, and that's voice or braille. And of course, this is a balance, right? We can have verbal and nonverbal cues. It says cure, including voice interfaces. A conversational interface can let you ask questions and get answers by breaking down semantic patterns into task options, for example. And there's another kind of sonification. That's what I just showed you was something that's commonly called audification. There are other kinds of sonification. There's something called ear cons. We're familiar with these too, but you probably don't know the term. Have you heard the term ear con?
No.
You've experienced them. So this is a brief, nonverbal, distinctive audio sound that represents a specific event or conveys feedback or other information to the user. So, for example, some of the use cases are like indicating event state, confirmation or errors, notification alerts, sets a landmark tone, sort of a context setting tone. You can also use it for sonic branding. Landmark tone could be the mood or some other, some way you're supposed to feel about the thing. So immediately, can you think of ear cons that you've heard?
Yeah, sure. The notifications that I get with the various bits of software that I use, particularly communication software, Outlook, Slack, they send me a tone, and they're different tones. So I know from one tone that I've got a Slack message and from another that I've got an Outlook message.
So that is a combination of notification and sonic branding, right?
Right.
So there are actually three kinds. What I call them all ear cons. They're not all ear cons. There's ear cons, auditory icons, and spear cons. So let me just give you an example of an ear con. Right? Mail was sent, right?
Yep.
It is structured, but it's abstract. That's not what sound sounds like. That's not what it sounds like when you put a letter in the mail, unless Australian mail is much more efficient than ours, right? But by hearing that sound again and again, we associate a particular activity with that sound, right? And so if I showed you this, if you use that app again and again, you know that means that the mail was sent.
Right.
Of the three, this is the least representative. Auditory icons, okay, crumpling paper, right? They are skeuomorphic, right? They represent natural sounds, and they're usually sonic caricatures. That doesn't really sound like paper crumpling. It evokes it, though. And what that says is, I'm crumpling something away up to throw it away, right? These are more distinct often than ear cons. And finally, we have spear cons. And you probably haven't seen these, but they will be familiar to you in concept. This is compressed speech, and I think I'm going to ask you what this reminds you of. Oops.
Elevator. Elevator.
So these are really useful. It's compressed speech. It helps a little bit less with the cognitive overload of hearing speech, right? It is sort of a speechy thing. It is speech, right? But they're not that widely used. But apparently studies have shown they're very distinct. You don't need to learn them. It is what it is. So if I'm walking around and I hear
Elevator. Elevator.
I know what it is. It's an elevator, right? I'm near an elevator. What does that remind you of, though?
Well, it sounds to me like a screen reader.
It sounds like a screen reader, right? And from and at the rate that a screen reader user would be using it, right?
Yeah.
Oftentimes they will cut out a couple of sounds. They're quite compressed and speeded up, but all three of these are technically spear cons are verbal, but these are auditory ways of conveying. And you can imagine as you're going through a data viz, if you heard 2008, 2009, 2010, 2011, etc., if you heard it very quickly, right? There's a reason that screen reader users like turn the speech rate up, right? It's because of that many timbals. You've got this fast, non-interruptive way of speaking that you can get certain kinds of things. I wouldn't use spear cons everywhere, but they can be useful some places. So when you're thinking about designing your data visualization, think about, can you represent something with an ear con or an auditory icon or a spear con? Here's another way of representing a complex issue, audio maps. I'm going to set this up. This uses a combination of verbal and non-verbal audio in this example. And by the way, I'm going to be showing a video from Brandon Biggs from the Smith Kettlewell Eye Research Center. It uses, if you had headphones on, you would hear something different in each ear, right? It uses non-verbal audio, uses binaural positioning, 3D audio, to help orient the listener. And landmarks are features of the landscape that you're trying to navigate around. And each landmark can use either natural or symbolic sounds. So either auditory icons or ear cons, auditory icons, or spear cons, right? And the audio volume is increased with the closeness of the source. So as you get closer to something, the sound for that thing gets louder. It's coming from a particular direction, and it gets louder as you get close to it. And maybe more importantly, the audio volume is decreased with distance to source. In other words, as you're getting, as something starts receding away from you, it's less distracting because it's lower, right? And at a certain point, it just drops off. And that level of detail decreases the cognitive load. So a lot of blind people, when they're navigating, hearing this speech coming at them all the time is overwhelming, right? They're already dealing with the auditory landscape around them. And hearing speech telling them which way to go, et cetera, can be really distracting. And another nice thing about this feature is that it builds on real world and video game navigation skills that non-sighted people or low vision people have often come to rely on. So I'm going to show you this demo, and just as a setup, basically this is a person navigating a playground, and they're trying to get to something called the laser arc. All right. And you can hear these features. You can hear different things, different ear cons and audio icons being played as they're navigating around.
First person view.
And some text, right? Some sound, some speech.
Long ramp. Ava's bridge.
Okay.
Ground carousel.
25, 18.
Disc spinner.
Playground walkway.
Net spinner.
Laser harp is very far off, ahead and to the right. The nearest point is at 2846.
And you hear it getting louder and louder as you get closer
Laser
to it.
harp.
Grid view. Playground walkway, 2249. Laser harp, 2248. Playground click, 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 click. Net spinner, 2230.
All right, and that laser harp just now we can't even hear it anymore. But as we got closer and closer to it, you can. So this is another way of navigating topological space, and I think it's a really interesting idea because it doesn't rely as much on speech itself. It's more impressionistic. It's more visceral, right? So maps are very interesting. Oops. Well, I'm not sure what went on there, but maps are interesting. We have here a map of the 2020 election, and in the US, the presidential election, by county. So it shows you a bunch of counties, and they're colored light blue if they voted sort of like if they leaned Democratic, and dark blue if they were a strong Democratic outcome, and sort of pinkish if they leaned Republican, and strong red if they voted really strongly Republican. So, Ricky, what can you tell me about this image right off the top, right?
I guess I can see patterns there from my geography knowledge of the USA, that there's a lot of the blue sections are focused on large population centers.
So you're bringing that to it, right? You knew that there could be any number of things here, right? And you're right that largely the blue ones are population centers and the red ones are low population areas, right?
Right.
You brought some extra context to it, right? And that's great. But you can also see that the blue things are not, they're kind of isolated away for the most part from the red things, right? The red ones is a huge swath of the country. And the blue ones are sort of clustered closer to one another than they are.
Right, and along the coast.
And along the coast. And so you see, you can see that the blue ones, very rarely is there a blue section completely surrounded by red. They tend to cluster together, right? There happens to be some in Kansas and Missouri, I happen to be from Missouri, which is here in the sort of the center-ish, right? And I know personally, you've got St. Louis on the left here, Kansas City on the right, and in the middle, you have Columbia, Missouri, which is the major college town, right? I happen
Right.
to know that because of the context I bring to it. And I know the culture, right? And so I know why that section is blue when everything around it is red. Topology matters, right? A map is more than a list of items. Relative position between items can be important. So you cannot simply convey this by text. I could list all the counties, or I could organize them by state, but it's not going to give you the same information, right? So there are other techniques that are useful for conveying how close things are together. For example, when we talk about topology, immediately we start thinking about tactiles, right? Tactile maps were the norm for accessible maps up until the digital age, right? So here's an example of sort of a hybrid tactile map. This is on something called swell paper. It's printed out on paper, and the darker black something is, and the thicker it is, the more that paper is raised up, right? They put it under a heat lamp, and the black ink absorbs more heat, so that section raises up more. And you would take this swell paper and you would put it on top of a touch screen, and you could move your hand over it. So you have a combination of tactile. You can see those thick lines that represent the motorways, and they've got Braille labels right near them. And then you've got sort of a gray area that's kind of a little bit raised and tacky, and that's sort of the city center. This is a map of Vancouver. And then you have some wavy lines, and those wavy lines, that's the bay, right? That's water, right? So you could move your hand, and then you've got icons like an airport and some other icon. I'm not sure what that is, but as you move your finger over certain features, you could hear audio stuff like the sound of water, or you could hear the name of the piece of water. You mouse over a road, you could hear like traffic sounds, or you could just hear the name of the road, right? So this is a sort of a hybrid approach with tactiles that kind of works. You could also have embossers. View Plus, for example, makes embossers that print these out pretty quickly, right? But it does still have that sort of physical thing that you kind of need in some ways, or you don't need it necessarily, but it is very helpful. The tactile relationship, especially for things like maps or scatter plots. And of course, if you made a print style sheet of this, you could print out everything in Braille, for example. So enter into the scenario a new kind of display called refreshable pin displays. Now, we might be familiar already with Braille readers, right? It's a single line or maybe two lines of Braille text, right? Those are pretty expensive, but some people have them. In the US, actually only about 40% of blind people know Braille because of the way our school system has developed. And those people are going to probably get jobs more than other people, right? Because they actually have stronger textual skills. So it's a civil rights issue, really. Braille may seem out of date, but it actually really helps reinforce things like spelling and grammar and punctuation, where screen readers do not necessarily. So here's an example of the graffiti refreshable pin display, and this thing is I'm going to say it's like 60 pins by 90 pins, something like that. You can actually put pictures on that, and actually I've seen data visualizations portrayed on these, and they're actually very effective. You can have both Braille and fixed grid. Some of them have variable pin height, so you can have gradations. You can have tall pins, you can have low pins. They're really cool, but they're expensive. I think they're around $5,000, $6,000 at least.
Ooh.
Uh, which is, look, if this is the kind of thing you need, it's useful, but it's pricey. Phys Studio, along with ETS, Educational Testing Service, we created an open source Spark Braille library for common Braille displays. I'm going to show you a little quick demo of that. This is just an open source project that, let's see. All right. So Spark Braille is a little open source project. It takes a line chart, or actually it takes some numbers and it transforms them. So I've got an SVG chart, and then I've got the compressed SVG chart. It compresses each line into basically into one of 4 pins. And so here we have, I'll just generate a new chart real quick. Okay, so you can see, if you can see it, you can see that it makes a set of Braille lines. It uses a Braille display to simulate seeing a line chart or an area chart. And so as you run your fingers over, you actually can feel the trend of a chart. I have it on authority from my friend Jason from ETS that it's actually quite effective. And we've got the area chart on. Let's turn off. With the area chart on, it sort of shows the baseline, the center line, the 0 line. When I turn that off, it's just a representation. And it uses the 2 cells of a Braille display to set up a to set the dots. It basically sets the dots as if it were an image, as opposed to a character in Braille. So that's another way of using tactiles that is sort of web friendly, that we can still use digitally today. And then finally, for the sort of this digital tactile stuff, we have vibro audio interfaces. There is a standard that I helped work on called the W3C Web Vibration API. And it vibrates the whole phone. So, when your phone gets a notification, you get a vibration. And as you run your finger over your phone, but it only does this as you go over an area, right? And so it feels like it actually sort of feels like if you time this correctly, just as you go over a line, for example, you start it and stop it immediately. It sort of feels like your finger is going over. It simulates a tactile experience. It's low resolution, but it does work, and it actually can convey senses of topology. And this is really good. But I think maybe, and there are people trying to make better touch screen things, but I think maybe the future of tactiles are these XR gloves, augmented reality, virtual reality gloves that are coming out, and they're going to be mass market, right? And basically they're gloves that simulate touch sensations. And I think that those things will probably be more active, more widely available than true tactile touch screens will in the near future, and cheaper as well. So, okay, so all of these technologies seem really cool, but how can we actually do these things? If we're on the web, how do we enable all this functionality? And the answer is, and I've just got a video clip of sort of a time rewinding episode of Twilight Zone on the screen there. The new Twilight Zone. It's a really good episode. So the answer as to how we enable all this functionality is text. I know I said that text is we want to use as little text as possible if we can, right? But the nice thing about text is that it's readable, selectable, indexable, searchable, findable, translatable. I've got a bunch of different fonts here. I've different styling. You can style the fill and stroke on SVG. SVG supports web fonts, for example. You can make text along a path. You can use it in your logos. And the key thing about text here is that text is the foundation of every piece of technology I showed you before. You start with visible text labels and alt text, okay? And then you can add structure, tags, semantic attributes, and metadata. And that metadata can be in text, right? And once you have that text, once you have the numbers, for example, then you can transform those into sound. Then you can transform those into tactiles. APIs like the web audio or vibration API can read the text and transform it into other modalities. And this sort of builds on the classic semantics versus presentation pattern. Once we have the text, then we can manipulate it. Once we have the numbers, then we can represent them in a number of ways. So the accessibility API, this is how, with a web browser, we don't just go we go from a document with all its text in it, right? We go from this document and then it goes into the DOM, the document object model. And that's presented directly to a sighted user visually. It's portrayed on the screen, right? But with the accessibility APIs, we actually have, it's a little more circuitous, right? So from accessibility APIs for screen reader users, it goes from the DOM to something called the accessibility tree, which is not exactly like the DOM. It's part of the DOM, but it's also augmented from the DOM. And then that goes through the operating system's accessibility API. And then that goes to the AT, like a screen reader. And then that goes to the user. So it's actually a more circuitous route. But what we can do is we can intercept this modality at any point and add these extra auditory or tactile features. So it really is useful to think of a data visualization as a document. Both of them have a title, as I talked about before. They could have provenance, like where the data is from, right? In the byline for a document. The intro paragraph on a document is, setting the context. And for a data visualization, that is, as I mentioned before, the X and the Y axis. The body, in the case of a document, is the three or four paragraphs of the text. And for data visualization, it's the data itself, right? It's all the things that support your conclusion. And the conclusion is on a document, it's the last bit, it's the last paragraph of your essay, for example. But in data visualization, the conclusion, is the insight that the reader has gained or the decisions that they have made based on getting information, right? So there's actually a strong correlation between documents and data visualizations. And then we can talk a little bit, about the anatomy of that chart, right? In addition to its structure, like a data visualization, like a document rather. Here's how we want to portray a chart. So we want to, how we want to expose it, how we want to provide affordances for a chart. We want to expose each landmark. That's, the title, the axes, the individual data points. We want to expose each landmark in a sequence to provide context. Right. So here, that's the title, the axes, etc. Now we want to show each data point in order and associate it with its axis label so that when you aren't just looking at something that says 325, a bar that says 325, you're associating it with a particular year, 1971 to 1980, for example, right? And then you can mark up each element with its role using role, class, and data attributes. I talk about this on my blog. And then you can embed the data in the chart in a structured way associated with its visual element, such that it can be extracted and read by a screen reader or your interpreter, right? And then you can derive and expose statistical information to allow the user to accomplish common tasks, like giving them the high or the low or the range or the total or the mean, or if you can, the trend line, right? So that's how we could be thinking about data visualizations. And again, I want to say, to me, a data visualization is a user interface for data. And there are different kinds of data visualizations, and they're optimized for performing different tasks, like the comparison to a whole, or comparison to other data points, or trends over time, or breakdown of categories, or connections between items, topologically or otherwise, and navigation and focus. These are all issues that you need to think about providing affordances for. And our mission, Phys Studio's mission, is to make implicit interactions, things that are implied, make them into explicit actions that give the power to question and to answer to everybody. And that is my presentation. Thank you for your attention. If you're interested in hearing about our Phys charts, if you're interested in seeing a webinar, if you're interested in contacting me about helping you with DataViz, please reach out. My email is doug@phys.studio. My website is phys.studio. And I'm Shepazu, SHEPAZU, on pretty much any social media platform, GitHub, etc. And that's what I got. Ricky?
That's fantastic, Doug. That is absolutely great. Thank you very much for that. That certainly makes me think about data visualization in a different way. And I know when I'm kind of looking at marking up a chart or a graph so that people with disabilities can access it properly, I'll be thinking about it in a slightly different way now, apart from trying to translate the detail, trying to translate the relationships between the data. That's fantastic. Thank you very much.
My pleasure. Thank you so much. Have a great conference.